A steam engine is a heat engine that performs mechanical work using steam as its working fluid. Steam engines are external combustion engines, where the working fluid is separate from the combustion products. Non-combustion heat sources such as solar power, nuclear power, or geothermal energy may be used. The ideal thermodynamic cycle used to analyze this process is called the Rankine cycle. In the cycle, water is heated and transforms into steam within a boiler operating at a high pressure. When expanded through pistons or turbines, mechanical work is done. The reduced pressure steam is then condensed and pumped back into the boiler. In general usage, the term steam engine can refer to either the integrated steam plants such as railway steam locomotives and portable engines, or may refer to the piston or turbine machinery alone, as in the beam engine and stationary steam engine. Specialized devices such as steam hammers and steam pile drivers are dependent on the steam pressure supplied from a separate boiler. Using boiling water to produce mechanical motion goes back over 2,000 years, but early devices were not practical. The Spanish inventor Jerónimo de Arias y Beaumont obtained the first patent for a steam engine in 1606. In 1698, Thomas Savery patented a steam pump that used steam in direct contact with the water being pumped. Savery's steam pump used condensing steam to create a vacuum and draw water into a chamber, and then applied pressurized steam to further pump the water. Thomas Newcomen's atmospheric engine was the first commercial true steam engine using a piston, and was used in 1712 for pumping in a mine. In 1781, James Watt patented a steam engine that produced continuous rotary motion. Watt's 10-horsepower engines enabled a wide range of manufacturing machinery to be powered. The engines could be sited anywhere that water and coal or wood fuel could be obtained. By 1883, engines that could provide 10,000 horsepower had become feasible. The stationary steam engine was a key component of the Industrial Revolution, allowing factories to locate where water power was unavailable. The atmospheric engines of Newcomen and Watt were large compared to the amount of power they produced, but high-pressure steam engines were light enough to be applied to vehicles such as traction engines and the railway locomotives. Reciprocating piston-type steam engines remained the dominant source of power until the early 20th century, when advances in the design of electric motors and internal combustion engines gradually resulted in the replacement of reciprocating steam engines in commercial usage, and the ascendancy of steam turbines in power generation. Considering that the great majority of worldwide electric generation is produced by turbine-type steam engines, the steam age is continuing with energy levels far beyond those of the turn of the 19th century. History. Early designs and modifications. The Eolipile, described by Hero of Alexandria in the 1st century AD, is considered to be the first recorded steam engine. Torque was produced by steam jets exiting the turbine. Thomas Savery, in 1698, patented the first practical atmospheric pressure steam engine of 1 horsepower. It had no piston or moving parts, only taps. It was a fire engine, a kind of thermic siphon in which steam was admitted to an empty container and then condensed. The vacuum thus created was used to suck water from the sump at the bottom of the mine. The fire engine was not very effective and could not work beyond a limited depth of around 30 feet. Thomas Newcomen, in 1712, developed the first commercially successful piston steam engine of 5 horsepower. Its principle was to condense steam in a cylinder, thus causing atmospheric pressure to drive a piston and produce mechanical work. James Watt, in 1781, patented a steam engine that produced produced continued rotary motion with a power of about 10 horsepower. It was the first type of steam engine to make use of steam at a pressure just above atmospheric to drive the piston, helped by a partial vacuum. It was an improvement of Newcomen's engine. Richard Trevithick. It was only after the invention of the lightweight, high-pressure steam engine by Richard Trevithick in 1797 to 1799 that steam engines became small enough to be used in smaller businesses and for use in steam locomotives. Since the early 18th century, steam power has been applied to a variety of practical uses. At first it powered reciprocating pumps, but from the 1780s rotative engines began to appear, driving factory machinery such as spinning mules and power looms. At the turn of the 19th century, steam-powered transport on both sea and land began to make its appearance, becoming more dominant as the century progressed. Steam engines can be said to have been the moving force behind the Industrial Revolution and saw widespread commercial use, driving machinery in factories, mills and mines, powering pumping stations, and propelling transport appliances such as railway locomotives, ships, steamboats, and road vehicles. The use in agriculture led to an increase in the land available for cultivation. There have at one time or another been steam-powered farm tractors, motorcycles, and even automobiles as the Stanley steamer. The weight of boilers and condensers generally makes the power-to-weight ratio of a steam plant lower than for internal combustion engines. For mobile applications, steam has been largely superseded by internal combustion engines or electric motors. However, most electric power is generated using steam turbine plant, so that indirectly the world's industry is still dependent on steam power. Recent concerns about fuel sources and pollution have incited a renewed interest in steam, both as a component of cogeneration processes and as a prime mover. This is becoming known as the advanced steam movement. Early experiments. The history of the steam engine stretches back as far as the 1st century AD, the first recorded rudimentary steam engine being the eolipile, described by Greek mathematician Hero of Alexandria. In the following centuries, the few steam-powered engines known were, like the eolipile, essentially experimental devices used by inventors to demonstrate the properties of steam. A rudimentary steam turbine device was described by Tachialdian in 1551 and by Giovanni Branca in 1629. Geronimo de Ariens y Beaumont received patents in 1606 for 50 steam-powered inventions, including a water pump for draining inundated mines. Denis Papin, a Huguenot refugee, did some useful work on the steam digester in 1679, and first used a piston to raise weights in 1690. Pumping engines. The first commercial steam-powered device was a water pump, developed in 1698 by Thomas Savery. It used condensing steam to create a vacuum which was used to raise water from below, then it used steam pressure to raise it higher. Small engines were effective, though larger models were problematic. They proved only to have a limited lift height and were prone to boiler explosions. It received some use in mines, pumping stations, and for supplying water wheels used to power textile machinery. An attractive feature of the Savery engine was its low cost. Bento de Moura, Portugal, introduced an ingenious improvement of Savery's construction to render it capable of working itself, as described by John Smeaton in the Philosophical Transactions published in 1751. It continued to be manufactured until the late 18th century. One engine was still known to be operating in 1820. Piston steam engines. The first commercially successful true engine, in that it could generate power and transmit it to a machine, was the atmospheric engine, invented by Thomas Newcomen around 1712. It was an improvement over Savory's steam pump, using a piston as proposed by Papin. Newcomen's engine was relatively inefficient, and in most cases was used for pumping water. It worked by creating a partial vacuum by condensing steam under a piston within a cylinder. It was employed for draining mine workings at depths hitherto impossible, and also for providing a reusable water supply for driving water wheels at factories sited away from a suitable head. Water that had passed over the wheel was pumped back up into a storage reservoir above the wheel. In 1720, Jacob Leupold described a two-cylinder high-pressure steam engine. The invention was published in his major work, Theatri Machinarium Hydraulicarum. The engine used two heavy pistons to provide motion to a water pump. Each piston was raised by the steam pressure and returned to its original position by gravity. The two pistons shared a common four-way rotary valve connected directly to a steam boiler. The next major step occurred when James Watt developed an improved version of Newcomen's engine, with a separate condenser. Boulton and Watt's early engines used half as much coal as John Smeaton's improved version of Newcomen's. Newcomen's and Watt's early engines were atmospheric. They were powered by air pressure pushing a piston into the partial vacuum generated by condensing steam. Instead of the pressure of expanding steam, the engine cylinders had to be large because the only usable force acting on them was due to atmospheric pressure. Watt proceeded to develop his engine further, modifying it to provide a rotary motion suitable for driving factory machinery. This enabled factories to be sited away from rivers, and further accelerated the pace of the Industrial Revolution. High-pressure engines. Watt's patent prevented others from making high-pressure and compound engines. Shortly after Watt's patent expired in 1800, Richard Trevithick and, separately, Oliver Evans in 1801 introduced engines using high-pressure steam. Trevithick obtained his high-pressure engine patent in 1802, and Evans had made several working models before then. These were much more powerful for a given cylinder size than previous engines and could be made small enough for transport applications. Thereafter, technological developments and improvements in manufacturing techniques resulted in the design of more efficient engines that could be smaller, faster, or more powerful, depending on the intended application. The Cornish engine was developed by Trevithick and others in the 1810s. It was a compound cycle engine that used high-pressure steam expansively, then condensed the low-pressure steam, making it relatively efficient. The Cornish engine had a irregular motion and torque through the cycle, limiting it mainly to pumping. Cornish engines were used in mines and for water supply until the late 19th century. Horizontal stationary engine. Early builders of stationary steam engines considered that horizontal cylinders would be subject to excessive wear. Their engines were therefore arranged with the piston axis vertical. In time, the horizontal arrangement became more popular, allowing compact but powerful engines to be fitted in smaller spaces. The acme of the horizontal engine was the Corliss steam engine, patented in 1849, which was a four-valve counterflow engine with separate steam admission and exhaust valves and automatic variable steam cut-off. When Corliss was given the Rumford Medal, the committee said that no one invention since Watt's time has so enhanced the efficiency of the steam engine. In addition to using 30% less steam, it provided more uniform speed due to variable steam cut-off, making it well suited to manufacturing, especially cotton spinning. Road vehicles. The first experimental road-going steam-powered vehicles were built in the late 18th century, but it was not until after Richard Trevithick had developed the use of high-pressure steam around 1800 that mobile steam engines became a practical proposition. The first half of the 19th century saw great progress in steam vehicle design. and by the 1850s it was becoming viable to produce them on a commercial basis. This progress was dampened by legislation which limited or prohibited the use of steam-powered vehicles on roads. Improvements in vehicle technology continued from the 1860s to the 1920s. Steam road vehicles were used for many applications. In the 20th century, the rapid development of internal combustion engine technology led to the demise of the steam engine as a source of propulsion of vehicles on a commercial basis, with relatively few remaining in use beyond the Second World War. Many of these vehicles were acquired by enthusiasts for preservation, and numerous examples are still in existence. In the 1960s, the air pollution problems in California gave rise to a brief period of interest in developing and studying steam-powered vehicles as a possible means of reducing the pollution. Apart from interest by steam enthusiasts, the occasional replica vehicle, and experimental technology, no steam vehicles are in production at present. Marine engines. Near the end of the 19th century, compound engines came into widespread use. Compound engines exhausted steam into successively larger cylinders to accommodate the higher volumes at reduced pressures, giving improved efficiency. These stages were called expansions, with double and triple expansion engines being common, especially in shipping where efficiency was important to reduce the weight of coal carry. Steam engines remained the dominant source of power until the early 20th century, when advances in the design of electric motors and internal combustion engines gradually resulted in the replacement of reciprocating steam engines, with shipping in the 20th century relying upon the steam turbine. Steam locomotives. As the development of steam engines progressed through the 18th century, various attempts were made to apply them to road and railway use. In 1784, William Murdoch, a Scottish inventor, built a prototype steam road locomotive. An early working model of a steam rail locomotive was designed and constructed by steamboat pioneer John Fitch in the United States, probably during the 1780s or 1790s. His steam locomotive used interior bladed wheels guided by rails or tracks. The first full-scale working railway steam locomotive was built by Richard Trevithick in the United Kingdom, and on the 21st of February 1804, the world's first railway journey took place as Trevithick's unnamed steam locomotive hauled a train along the tramway from the Penwydarren Ironworks, near Merthyr Tydfil, to Abercynon in South Wales. The design incorporated a number of important innovations that included using high-pressure steam, which reduced the weight of the engine and increased its efficiency. Trevithick visited the Newcastle area later in 1804, and the colliery railways in northeast England became the leading centre for experimentation and development of steam locomotives. Trevithick continued his own experiments using a trio of locomotives, concluding with the Catchmere-Hocken in 1808. Only 4 years later, the successful twin-cylinder locomotive Salamanca by Matthew Murray was used by the edge-railed rack and pinion Middleton Railway. In 1825, George Stephenson built the locomotion for the Stockton and Darlington Railway. This was the first public steam railway in the world, and then in 1829, he built the Rocket, which was entered in and won the Rainhill trials. The Liverpool and Manchester Railway opened in 1830, making exclusive use of steam power for both passenger and freight trains. Steam locomotives continued to be manufactured until the late 20th century in places such as China and the former East Germany. Steam turbines. The final major evolution of the steam engine design was the use of steam turbines starting in the late part of the 19th century. Steam turbines are generally more efficient than reciprocating piston-type steam engines, have fewer moving parts, and provide rotary power directly instead of through a connecting rod system or similar means. Steam turbines virtually replaced reciprocating engines in electricity generating stations early in the 20th century, where their efficiency, higher speed appropriate to generator service, and smooth rotation were advantages. Today most electric power is provided by steam turbines. In the United States 90% of the electric power is produced in this way using a variety of heat sources. Steam turbines were extensively applied for propulsion of large ships throughout most of the 20th century. Present development, although the reciprocating steam engine is no longer in widespread commercial use, various companies are exploring or exploiting the potential of the engine as an alternative to internal combustion engines. The company Energy Project AB in Sweden has made progress in using modern materials for harnessing the power of steam. The efficiency of Energy Project's steam engine reaches some 27 to 30% on high-pressure engines. It is a single-step, 5-cylinder engine with superheated steam and consumes approx. 4 kilograms of steam per kWh. Components and accessories of steam engines. There are two fundamental components of a steam plant: the boiler steam generator, and the motor unit, referred to itself as a steam engine. Stationary steam engines in fixed buildings may have the boiler and engine in separate buildings some distance apart. For portable or mobile use, such as steam locomotives, the two are mounted together. The widely used reciprocating engine typically consisted of a cast-iron cylinder, piston, connecting rod and a crank and flywheel, and miscellaneous linkages. Steam was alternately supplied and exhausted by one or more valves. Speed control was either automatic, using a governor, or by a manual valve. The cylinder casting contained steam supply and exhaust ports. Engines equipped with a condenser are separate type than those that exhaust to the atmosphere. Other components are often present: pumps to supply water to the boiler during operation, condensers to recirculate the water and recover the latent heat of vaporization, and superheaters to raise the temperature of the steam above its saturated vapor point, and various mechanisms to increase the draft for fireboxes. When coal is used, a chain or screw stoking mechanism and its drive engine or motor may be included to move the fuel from a supply bin to the firebox. See mechanical stoker heat source. The heat required for boiling the water and supplying the steam can be derived from various sources, most commonly from burning combustible materials with an appropriate supply of air in a closed space. In some cases the heat source is a nuclear reactor, geothermal energy, solar energy, or waste heat from an internal combustion engine or industrial process. In the case of model or toy steam engines, the heat source can be an electric heating element. Boilers are pressure vessels that contain water to be boiled, and some kind of mechanism for transferring the heat to the water so as to boil it. The two most common methods of transferring heat to the water are water tube boiler. Water is contained in a run-through one or several tubes surrounded by hot gases. Fire tube boiler. The water partially fills a vessel below or inside which is a combustion chamber, a furnace, and fire tubes through which the hot gases flow. Fire tube boilers were the main type used for early high-pressure steam, but they were to a large extent displaced by more economical water tube boilers in the late 19th century for marine propulsion and large stationary applications. Once turned to steam, many boilers raise the temperature of the steam further, turning wet steam into superheated steam. This use of superheating avoids the steam condensing within the engine and allows significantly greater efficiency. Motor units in a steam engine, a piston, a steam turbine, or any other similar device for doing mechanical work takes a supply of steam at high pressure and temperature and gives out a supply of steam at lower pressure and temperature, using as much of the difference in steam energy as possible to do mechanical work. These motor units are often called steam engines in their own right. They will also operate on compressed air or other gas. Cold sinkers with all heat engines. A considerable quantity of waste heat at relatively low temperature is produced and must be disposed of. The simplest cold sink is to vent the steam to the environment. This is often used on steam locomotives, as the released steam is vented up the chimney so as to increase the draw on the fire, which greatly increases engine power, but reduces efficiency. Sometimes the waste heat is useful itself, and in those cases very high overall efficiency can be obtained. For example, combined heat and power systems use the waste steam for district heating, where CHP is not used. Steam turbines in stationary power plants use surface condensers as a cold sink. The condensers are cooled by water flow from oceans, rivers, lakes, and often by cooling towers which evaporate water to provide cooling energy removal. The resulting condensed hot water is then pumped back up to pressure and sent back to the boiler. A dry-type cooling tower is similar to an automobile radiator and is used in locations where water is costly. Waste heat can also be ejected by evaporative cooling towers used past the rejected to external water cycle that evaporates some of flow to the air. Cooling towers often have visible plumes due to the evaporated water condensing into droplets carried up by the warm air. Evaporative cooling towers need less water flow than once-through cooling by river or lake water of 700 megawatt coal-fired power plant may use about 3,600 cubic meters of make-up water every hour for evaporative cooling, but would need about 20 times as much if cooled by river water. In all cases, the steam plant water, which must be kept pure, is kept separate from the cooling water or air, and once the low-pressure steam condenses into water, it is returned to the boiler. Water pump. The Rankine cycle and most practical steam engines have a water pump to recycle or top up the boiler water, so that they may be run continuously. Utility and industrial boilers commonly use multi-stage centrifugal pumps. However, other types are used. Another means of supplying lower pressure boiler feed water is an injector, which uses a steam jet usually supplied from the boiler. Injectors became popular in the 1850s but are no longer widely used, except in applications such as steam locomotives. It is the pressurization of the water that circulates through the steam boiler that allows the water to be raised to temperatures well above 100 degrees Celsius, boiling point of water at 1 atmospheric pressure, and by that means to increase the efficiency of the steam cycle. Monitoring and control. For safety reasons, nearly all steam engines are equipped with mechanisms to monitor the boiler, such as a pressure gauge and a sight glass to monitor the water level. Many engines, stationary and mobile, are also fitted with a governor to regulate the speed of the engine without the need for human interference. The most useful instrument for analyzing the performance of steam engines is the steam engine indicator. Early versions were in use by 1851, but the most successful indicator was developed for the high-speed engine inventor and manufacturer Charles Porter by Charles Richard and exhibited at London Exhibition in 1862. The steam engine indicator traces on paper the pressure in the cylinder throughout the cycle, which can be used to spot various problems and calculate developed horsepower. It was routinely used by engineers, mechanics and insurance inspectors. The engine indicator can also be used on internal combustion engines. See image of indicator diagram below. Governor. The centrifugal governor was adopted by James Watt for use on a steam engine in 1788 after Watt's partner Boulton saw one on the equipment of a flour mill Boulton and Amp Watt were building. The governor could not actually hold a set speed, because it would assume a new constant speed in response to load changes. The governor was able to handle smaller variations such as those caused by fluctuating heat load to the boiler. Also, there was a tendency for oscillation whenever there was a speed change. As a consequence, engines equipped only with this governor were not suitable for operations requiring constant speed, such as cotton spinning. The governor was improved over time and coupled with variable steam cut-off. Good speed control in response to changes in load was attainable near the end of the 19th century.